Okay, and here I will share with you how we are going to actually do the, let me just get rid of this. Okay, how we are going to calculate an electric field of distribution of charge. Distribution of charge means like it's not a single, it's not a point charge. It is a continuous distribution of charge. This might be a rod that is charged. It might be a disk. It might be a ring like this one. And here, charge Q is uniformly distributed around a conducting ring of radius A. Here, we need to know that, again, we need the basic knowledge of geometry, laws of, let's say, areas, circumferences, in this type of course. Find the electric force, the electric field at point P on the ring axis at a distance x from its center. And here you can see we will dissect that ring into like these kind of small pieces, each having a length of ds and holding a charge of dq. It's at a distance r from p, which we can find r as the square root of x squared plus a squared, because this is x, this is a. One more thing, like the electric field, we are going to say is gonna be like, we're gonna imagine there is a test charge, and then this is the direction for the electric field. If you will find the components, then you're gonna find that the dex is going to be in this direction, and then dey is going to be in this direction. And if we are going to consider the one on the opposite side, I will say this is what we are going to get for the electric field. Then this is going to be dE, and it's going to be by symmetry, it's equal. And then I'm going to have the dEy in this direction and the dex in this direction. These they're gonna accumulate, and these they're gonna cancel, and therefore we can conclude simply that the electric field here is going to be along the x-axis only. Now I can say that in the textbook they define something called lambda, which is the charge per unit length, q over 2 pi a. I preferred maybe to use this notation here, and then dq is going to be lambda times this length ds. Then you're gonna find what is really the charge that is in this section. Okay, then here dE is gonna be the electric field, k the electric constants, times dq over r squared. I substituted my value. This is my value for dq, and this is my ds here. Okay, and this is really here my 1 over r squared, and this is my k. When I squared, this is x squared plus a squared. Remember, dex is going to be de cosine the angle. Okay, therefore, I need to find what is cosine alpha. Cosine alpha from the diagram, it's like if you remember, this is square root of x squared plus a squared, and this is x, then, and I'm looking for theta, then it's the adjacent divided by the hypotenuse. And then I integrated. Remember, all these, they're gonna be constants, and I need to integrate ds from 0 to 2 pi a, and I will say this is the result here. And I know that it's gonna be along the x-axis, therefore this is the solution for this one. Now I can move to another example here where I have again positive charge is distributed uniformly along the y-axis between y equal negative a and y equals positive a. Find the electric field at point B on the x-axis at the distance x from the origin. Again, we are going to do the same thing. We are going to dissect that thing that I can see here into small regions, and this is a line segment, and therefore I will say I'm gonna have divide the line charge into small segments, each is dy. Okay, and that dy, again, we are going to use lambda as here q, because the length of it is 2a. It's going to be q over 2a, and therefore dq is going to be that lambda, which is q over 2a times dy. And then I can say that the electric field is going to be k dq over r squared, which means is going to be k q over 2a, and then here dy over x squared plus y squared. The same, like it's very similar. Now I will say that again here the dE can be split into dEx and dEy, and that one is gonna be dE cosine alpha, and dEy is gonna be dE sine alpha, and alpha here it is x over r. And I will say this is actually cosine alpha, and sine alpha can be written as y over r. Then I can here find dEx as k q over 2a, and this is x dy divided by x squared plus y squared. This is 3 over 2, and the y components is going to be negative k q over 2a y dy over x squared plus y squared 3 halves. After that, of course, I need to integrate, and when I integrate the from, of course, negative a to a, I'm gonna get 4ex q over 4 by epsilon naught, which is the 1 over that is gonna k 1 over x square root of x squared plus a squared, and for ey I'm gonna get a 0. Okay, because this is how it's gonna be, and then my e is gonna be 1/4 by epsilon 0 q over x square root of x squared plus a squared times I. Okay, then it is a very consistent method where you are going to define first what is your lambda, what is dq, integrate, and sometimes we might ask you to have a special form. Okay, here, okay, I have one of the checkpoints that I have a positive charge Q, that it is distributed uniformly along the x-axis from x equals 0 to x equals a, and I have a positive charge that is located on the positive x-axis at a distance x equals a plus r from the origin. And we want to calculate what is really the x and y component of the electric field produced by the charge distribution at points on the x-axis where x all right, then at that point again here I will do the same thing. I will have the charge distribution that can be divided into small distances and each holding dq charge, and here the distance between the point and the segment, it is x minus x prime. I did integrate, and of course here also by symmetry EY is going to be 0. And the second question is asking calculate the force, magnitude, and direction that the charge distribution exerts on the charge Q. Then here you are going to use we have EX, then I can say F is going to be Q times E, and then this is going to be the expression. Okay, I will upload also these notes. Maybe like some of the examples I did not complete with the video, but you're gonna have them uploaded as notes. Thank you very much and have a great day.